This last video, what we're going to do is we're going to go ahead and try to convert some of these spherical equations to the rectangular types of equations to make it a little bit easier to understand what these might look like. Some of the techniques that we use to be able to convert cylindrical are going to be used for spherical. Case in point, we have this rho equals 3. So what we can do is we can square both sides. You might remember we did this with cylindrical coordinates. So we get rho squared is equal to 9. We know that rho squared is x squared plus y squared plus z squared. And clearly this is our sphere. Radius is 3. Center is at the origin. If we were to graph it, just something like this, where radius is 3. All right, so that's a pretty easy one. So if you ever have rho is equal to a constant, automatically that's a simple way to write a sphere in spherical coordinates. Okay, really nice and easy, rather than having x squared plus y squared plus z squared. A second example, this theta equals 3 pi fourths. One of the techniques that we used earlier was just to take the tangent of both sides. So we could say tan of theta equals tan 3 pi fourths. We know that tan of theta is y over x. All right? Remember, theta is the same in both cylindrical and spherical coordinates. Tan of 3 pi fourths is -1. Right? If you don't believe me, you could certainly throw that into your calculator. Or we get y equals -x. Right? So essentially what we have is we have a slope of -1, right? And we could plot some points if we wanted to with this. But if we wanted to plot it in 3 dimensions, then what we would end up with is we'd end up with a plane, and the slope is going to be -1 of that plane. All right, so we know that certainly a point would be 1, -1 that lies on this plane. All right, so something like over here. All right, another point would be 2, -2. All right, and you guys can see what's going on with this. We get a plane that bisects this way. And again, it does run infinitesimally, so it runs this way as well. All right. So if you ever have theta equals a constant, in spherical coordinates, that's a plane. What if you have phi equals a constant? All right, well, that's a little bit more difficult. One of the relationships you might remember is that phi is the same thing as the arc cos of z over rho. So we could rewrite this as arc cos z over rho is equal to pi 6. Okay. And then we could go ahead and take the cosine of both sides. So z over rho equals cos of pi 6. Right? Cos of pi 6 is √3 over 2. Right? So we're just going to compute that. Right. And then I'm going to square both sides of this. And the reason I'm going to square both sides is because of the rho. All right. I like to be able to convert back into Cartesian coordinates, we have to have rho squared. So if I square both sides, z square over rho square is going to be equal to 3/4. And we're getting closer. I'm going to multiply both sides by 4 rho squared. So we're going to get that 4z squared is going to be equal to 3 rho squared. And now we can see that we can convert rho squared. So we get 4z squared is going to be equal to 3x squared plus 3y squared plus 3z squared. Then we can subtract the z squared from the left-hand side, set it equal to 0, and we end up with 0 equals 3x squared plus 3y squared minus z squared. That's probably the most simplistic form that we can get. Now, what shape does this take? Well, that's where we have to go back to that quadratic surfaces sheet. Notice that it's set equal to 0. So it's on page 2 of the quadratic surfaces sheet. We have all quadratic, and we have one negative. Right? And if we go back to that sheet, on page 2, there's only one of the surfaces that has all quadratics and one negative, and that's going to be the elliptical cone. Right? So this is going to end up being a cone. It's centered at the origin, and it expands along the z-axis because z is the negative coefficient. Okay, so expands on z. If I were to graph that as best as I can, we probably get something like this. All right. So if you ever have phi is equal to a constant, that just winds up being a cone. All right. So three main shapes. If we have rho, that's equal to the sphere. Rho equals a constant. If we have theta equals a constant, that's a plane. And then if we have phi equals a constant, that's a cone. All right. Now the cones can be shifted, and sometimes we have to go through and do this process. Right? Now, what about this animal? Rho equals cos of phi. Right? One of the techniques that we saw earlier with respect to cylindrical coordinates was multiplying both sides by r. So let's multiply both sides by phi this time. I'm sorry, by rho, not phi. And the reason we do that is because, well, we know that there's a relationship between rho squared and the Cartesian coordinates. So that's x squared plus y squared plus z squared. And as you may remember by now, rho cos of phi is the same thing as z. Right? So that can be just written as 4z. And now for most of you, the writing's on the wall at this point because we can subtract 4z from both sides and complete the square. I'm going to take half of -4 and square it. So that means I'm going to add 4 to both sides. And when we complete this factorization, x squared plus y squared plus z minus 2 squared equals 4. That's a sphere. The center is at 0, 0, 2, and the radius is 2 for this. All right. If we were to graph this, we'd probably end up with something approximately like this. All right, so that's our sphere. It should be touching at the origin. I apologize. Again, screen is not the most fine tool to be working with. One last example. This is a really sneaky one. We have rho equals cosecant of phi. Now, if that was a sine or a cosine, this problem would be much, much easier. But because it's a cosecant, this is a really nasty one. But I do want to illustrate how you can try to sneak around and do this one. Remember the fact that x and y both have definitions. All right, so we have to utilize those definitions from Cartesian to spherical. So remember that x is equal to rho sine phi cos theta, and remember that y is equal to rho sine phi sine theta. Right? Now, what I'm going to do is I'm going to divide both sides, right? And I'm going to end up with sine. I'm going to divide both sides, excuse me, by sine of rho sine phi. And you're probably asking me why I would do that. Okay, so just hold on a moment and let me get there. So we have cos theta, and we have y over rho sine phi is equal to sine theta. All right. Now I'm going to square both sides of both of these equations. All right. So now we're getting really into the weeds of why would you even do this? And why would you do this? It's one of those things where you just have to try something. And because we know that there's some relationship between cos square and sine square, maybe we can use these Pythagorean relationships. So we get x squared over rho squared sine square phi is equal to cos squared theta. And also y squared over rho squared sine square phi is equal to sine square theta. If I add those together, and this is sort of eliminating the parameter, right? So you might remember that from calculus 2. You can add these together, and we would end up with x squared over rho squared sine square phi plus y squared over rho squared sine square phi is equal to cos square theta plus sine square theta, and by our Pythagorean relationship, that's equal to 1. If we knew what this was equal to, this rho sine square phi, we'd be in good shape. Now notice we never used the original equation. These are all identities that are generated from the fundamental definitions of converting spherical into rectangular coordinates. Well, another way to write this is to say that rho equals 1 over sine phi, multiply both sides by sine phi, and then square both sides. And what we can see is that rho square sine square is equal to 1 for this particular equation. And hence, we get a really nice equation finally that x squared plus y squared is equal to 1. And in 3 dimensions, in 2 dimensions it's the unit circle. In 3 dimensions it is a cylinder that expands on the z-axis because z is an element of the reals. It's undefined for us as a particular parameter. So if we were to graph it, approximately something like that. Cylinders are much more difficult to work with in spherical coordinates. Now we probably know that if I was to write this in cylindrical, we would get r equals 1. So it's much, much easier to deal with a cylinder in cylindrical coordinates than a cylinder in spherical coordinates, okay? So we much would rather not work with this rho cosecant of phi. Right, so hopefully this is a good introduction for you all to be able to work with the 2 new coordinate systems, cylindrical and spherical.